Okay, this is problem set on Newton's laws. And here is the first problem. On the screen, we'll read together. A 20 kilogram box rests on a table. What's the weight of the box? The weight of the box is, that's the box. The weight of the box is mg, and the normal reaction is Fn, right? Weight is always the force of gravity. So it's mass times acceleration due to gravity. You get it as 20 times 9.8, which is 196 newtons. And in this case, if you take the net force along the y-axis, you take the net force along the y-axis, it's 0, isn't it? Because the object is not moving. Therefore, Fn minus mg is 0, which makes Fn equal to mg, which makes that also 196 newtons. And I was saying this is 0 because the acceleration is 0. Because what's Newton's second law? The net force should be equal to mass times acceleration, isn't it? Now, is this object accelerating? No. That's why the acceleration is 0. That's why the right-hand side is 0. Okay, now let's go to the B part. In the B part, you have one box over the other, as shown. So that's the situation. You have the 20 kilogram, you have the 10 kilogram. But in the free body diagram, you have to learn to look at the forces acting on one object at a time. So right now, I'm only looking at the forces on the 20 kilogram, right? Correct? That is the weight of the 20 kilogram, and that is the normal force by the table on the 20 kilogram. Is there any other force on the 20 kilogram? Is there any other force? Yeah, there is.
Oh, well, now.
Okay. Because there's the 10 kilogram on top of the 20, yes, there is another force. So there are three forces. One's M2G, I'm calling the 20 kilograms M2, okay? M2G, which is its weight. Now, how do you read that? That is the force on 2 due to 1. Force on 2, that's the 20 kilogram, right? Force on the 20 due to the 10. All right, so that's how we label it, and that is the normal force on 2, Fn2. If you cannot see it, it's Fn2. Now let's look at the forces acting on the 10 kilogram box. Does it have its weight acting down?
Yes.
Yes, so you have its weight. I want it to go slowly so you get a chance. That's M1G. That's the weight of the 10 kilogram. Now, who can tell me what is this? Is this, yeah, that's a normal force, of course. Is that the table pushing up? No. It is the 20 kilogram box pushing back up on the 10 kilogram. How would we label that force? If this was F21, wouldn't this be F12? And don't you know that one is the reaction of the other? That means F21 and F12 are equal and opposite. That's a very important point there. They are pushing back. So that's Fn1, but that's the same as F12. I hope you understood that, correct? That is a normal force, yes, but it is also the force applied on 1 due to 2. Now, if you get those diagrams correct, then it's easy. From this one, Fn1 minus M1G is equal to 0. So Fn1 is, I should have said M1G, which is 98. Is it 98? Because it's 10 times 9.8, correct? But at the same time, we know F11 is the same as F12, which is the same as F21 in magnitude. Is that right? Okay. So when you go back to this diagram, you already know F21 because F21 is the same as F12. Okay. Therefore, now looking at this diagram, Fn2 minus M2G minus F21 is 0. Let me stop it right there. Does that make sense?
Yeah, the notation for the second box on top of the big box, the little one, that's just like counter notation, right?
It is. It is the reaction. It is. But when you look at these forces along the y-axis, don't you see two down,
Yeah.
two forces down, and one up? That's why I took the upward force as positive and the two down forces as negative. You see this? And set them equal to 0. Now, just a matter of plugging in the numbers. We're trying to find Fm2, so take that to the other side. The math is really simple once you get the concept. But if you do not have the concept, the math is useless. So those are the answers to the velocity has got to be in meter per second. So do you know how to change? You got to multiply by 5 divided by 18. You get 26.4 meter per second. That's the initial velocity. And what is the final velocity? Okay. Delta t or t, 8 seconds, 8.0 seconds given. So now you know you could find the acceleration. And if you could find the acceleration, then you could calculate the mass. It's a calculate the force. Straightforward question, isn't it? Force is mass times acceleration. So let's finish this. And the equation you're going to use is V2 is V1 plus A times t, or simply the definition of acceleration, delta V by delta t. Take the difference, divide it by time, you would get negative, and the negative shows it's slowing down, 3.30 meter per second squared. Now, because it's slowing down, is this force an opposing force? Is it helping the motion, or is it impeding the motion? Is it resisting the motion? Come on now. What is it doing? Okay, so that's what you know, because A is negative. And therefore, the force is also going to be negative. And a negative force always shows it's against the motion. All right, so you take that mass, multiply it with the negative, and you get negative 3,600, which again means it's opposing the motion. Is this question talking about the fisherman just holding the fish right there? No. Let's imagine that he was just holding the fish there. What would have been the tension in the fishing line?
22 newtons.
No. 22 newtons is the breaking strength of the fishing line, right? My question was, if he was just holding it there, the tension would have been mg. Mg, right? Which would have been, do we know the mass of the fish? No. If we did know, surely that would have been less than 22. Are you able to visualize it? Now what is he doing? He's going against gravity. He's yanking it up. So what do you think? Will the tension increase in the string and the fishing line, or will it decrease? Increase. But if he was moving it down, it would decrease. So what's the formula for tension in this case? Already there's mg, and now he's yanking it up with an acceleration, so there must be an additional factor of m times a. That make any sense? Because that's the force that he is creating by yanking it up. So mg plus ma will be the new tension. But if he was moving it down, it would have been mg minus ma. Made sense, didn't it? Okay, so let's get this problem. That's the fish, cute little one. Tension Ft, mg is the weight. And you have to look at this and do it all the time this way. Net force is Ft minus mg, isn't it? Opposite direction, so Ft minus mg. And according to Newton's second law, that net force is equal to m times a. That's the only formula we're using. Net force is mass times acceleration. So you take that term to the other side. That's how you get that as positive. And it goes to the other side. That's why when you take the mass common out, you get g plus a. And therefore, you can rearrange and make mass the subject, and you would get Ft divided by g plus a, which is 22. That's the maximum it can take, isn't it? Divided by the sum of the two factors, and you get 22 divided by 12.3, 1.79 fish. Not so huge, but not too small either. At least I'm hoping you read the problem and visualize what's happening. In this case, it's baseball. That's the actual mass. It's traveling at 35 meters per second. Man, that's fast. And that's how those guys throw it, really fast. And strikes the catcher's mitt, which, in bringing the ball to rest, recoils backward 11 centimeters. You know what that means, right? Pulls the hand backwards 11 centimeters. What is the average force applied by the ball on the glove? Again, F is what you're looking for. And the only way you can get force is using the formula, mass times acceleration. The mass is given, you see? And so what you have to do is find the acceleration. And to find the acceleration, what are the quantities you know? Do you know the initial velocity?
Yes.
Yes, you know the initial velocity in proper units. You know the final, 0. You know the displacement, but it is in centimeters. You got to change it into meters. And you have to use the equation. Do you see that this is just chapter 3 or chapter 2, actually? Right? So let's finish it. Because we're still on the college physics level now, up to this problem. It's going to get better. Now, when I say this, you know how to read that. That is the force on the glove due to the ball. Action. Reaction is force on the ball due to the glove. Okay. You know, sometimes you may not notice the importance of this, but please look. What is this? This is the force on which object? Come on, force on which object? On the ball. So that's why you need the mass of the ball. See? Because there is going to be some case where you'll have two masses and you do not know which one to use. So please be careful. If you're calculating the force on something, you need the mass of that thing. Keep that in mind. So this is mass of the ball times acceleration of the ball. Mass of the ball is 0.14 kilograms. Initial velocity is 35.0 meter per second. Final is 0. Acceleration we do not know, but we can find that. And do you remember the equation we're going to use? Centimeters must be in meters. Anybody? It is the equation that doesn't have time in it. Thank you. That's correct. V2 squared minus V1 squared is 2a delta x, and make a the subject. Substitute the numbers there. Be a little careful. And when you get numbers, look at it and say, could it be that high? I mean, that's a big deceleration, isn't it? Yes or no? Could it be that high? Yes, because he stopped it in how many centimeters? You should never apply brakes to a car this way. You see that? But in this case, yes, it's so high because the stopping distance was really small. That's why. Do you think you can stop your car in 11 centimeters? That's what you think. You cannot. If you're driving at that speed, you cannot. And one of the reasons is the mass is really big. So its momentum is big. We'll come to that later on, okay? So that's very clear. Once you get the deceleration, just multiply it with the mass to find the force. Again, it's negative because it's an opposing force. But what does the question ask you? Is the question asking you the force applied by the glove on the ball? No, what did we find out? Maybe you're missing. What did we find out right now? We found out the force on the ball. But the question is asking you for force applied by the ball on the glove. Most students would stop it here and lose 2 points. You see that? But now you know, one is the action, the other is the reaction, so you take the opposite of that, you get full points for that. Well, unless you're jumping onto something like sand or maybe a mattress. Now listen to me, tell me, I gave you 3 examples. if you're having to jump onto concrete or something, that is solid, you got to bend your knees, right? But if you're jumping onto sand or something that is soft, you need not do that. But in both cases, you're doing something, knowingly or unknowingly. What are you doing? When you bend your knees, actually, what are you doing? Yes?
Saying the time that the force is being.
You said we're increasing the time. Yeah, we're increasing the time for you to stop. Because just before you hit, you have a certain velocity, don't you? And you're going to stop. Now the important thing is, if you delay the stopping, your acceleration, or in this case, your deceleration is going to be small. But if you stop like that, your deceleration is going to be so big, therefore the force on you will be huge, you'll have broken bones. Does that make sense? Yes. That is one of the reasons why when a baseball player catches the ball, he is not a fool, he will not catch it this way. That's a fool. Pushing his hand forward, he will actually, as he catches it, draw it backward. He's doing the same thing. He's giving it more time to stop. You see that? So that's so useful all the time. Therefore, it comes back to, actually there are two problems in one here. Did you read it? Did you read it? All right, if you did, what's your idea?
Find time.
Find the time? What you're looking for is the velocity just before his feet strikes the ground, right? We're looking for that. I want to take more time on this. So how do you do it? Yes?
Do you find the velocity before you subtract the 3.9 meters from, you subtract the 0.7 meters from that?
No.
You would find the velocity at the 3.9 and then the velocity at the 0.7, since there's more time for those 0.7 meters.
You're trying, but I don't know whether you're saying,
Saying it correctly?
yeah, maybe you have the idea, but I don't know whether you. Anybody? You have to surely see that these are two different cases. You cannot mix them up. Two different cases. Let me show you the difference. Case one. What's his initial velocity when he's on the roof?
0.
Okay. And it's coming down. Isn't he a freely falling object? So what's the acceleration? 9.8 meters per second squared. Okay, so you have the initial velocity, you have the acceleration, you have the distance, 3.9 meters. Couldn't you find the final velocity?
Yes.
Wouldn't that be the velocity just before hitting the ground? Whew. That was easy. Now, second case. Listen, second case. The final velocity of the first case is the initial velocity of the second case. Now, how many understood? Thanks. Some did not. What do? He's at rest. He's coming down. He's speeding up, right? He's just about to hit the ground. He has a maximum velocity. That's case one. End of case one. Now, beginning of case two. Because from there, he's going to slow down and his velocity is going to become
0.
within a distance of 0.7 meters. That's case two. So doesn't he have a deceleration during that second part? Can we find the deceleration? Yes, we can. If you get the deceleration, force is mass times that deceleration, done. Do it. I'll do the math for you. That's where we save time. I do not want you to calculate. This is what I was saying in case one. And the equation is v2 squared is v1 squared plus 2a delta y. Initial velocity is 0, so that term is gone. Of course, you have to take the square root of that. You will get 8.7 meter per second. That is the velocity with which his feet will strike the ground. Now, case 2, that becomes the initial velocity. That's why it's v naught. Case 2. His final Okay, I'm using V1, V2 here. Final is 0. Delta Y is 0.7 meter. A is what we're trying to find. Same equation. Negative 54, and therefore net force, if at all you had got up to this part, still you would have missed the last part, probably. Now you have already seen it. In the last part, most of you would have gone by mass times acceleration, correct? Be honest. And then you have forgotten about his weight. When he hits the ground, listen, it's not just the force due to his acceleration, but his weight is also there, correct? If he's just standing there, isn't he applying a force? Yeah.
Yes.
So that force is still there. And on top of that, because of his deceleration, there is an extra force. So the total force, the net force, would be the sum of the two. Now, how do I bring it out? When he hits the ground, you have two forces. mg is his weight, down. ft is up, or fn. I should have called it fn because it's a solid surface, normal force. So mg minus ft, as I'm showing you, I don't know why I called it ft anyway. That should be equal to m times a. So ft or fn is mg minus ma. So mg minus a, this case, so
You just replaced FT with MA?
no. Let me explain again. Which force is greater, mg or ft? In this case, which is greater?
MG.
So that's how you take the sum always. Take mg minus ft is equal to ma, but yet when you substitute for a, it's negative. So in the end, it becomes plus. As long as you have the logic is the force must be greater than his weight, isn't it? That's the logic. So if you only follow math, you're going to make a mistake. If you have the logic, it's going to be correct. Yes. Both are 3.2. Okay. And I'm trying to show you the tensions. I'm calling those 1 and 2. The top one is 1. The lower one is 2. And then I'm saying I'm going to draw the forces acting on the lower one. That's why, that's this bucket. And what are the forces acting on that bucket? It's weight and the tension in this part of the string, isn't it? That's all. So those two, mg and ft, they call it ft1, but probably I'll change it because I thought I was calling this 2. I should have called it ft2. Anyways, going back to this one, what are the forces again? Now you see there are two forces down, and you know why. One is its weight, the other is the reaction of the tension, isn't it? Okay, mg, so you have ft2 and you have ft1. I'm trying to say that this is the action. Look at that. Look at these two. Do you see this? Reactions, and then this. So these are the forces acting on the top one, or in this part of the string. 3 forces. All right, what's the net force here? Net force. Net force is 0 if it's at rest, right? But it's actually ft1 minus mg, so set that equal to 0. Net force is ft1 minus mg, set it equal to 0. Therefore, ft1 is mg. Definitely. That's 3.2 times 9.8. Yeah, I think I looked at significant figures. So 31 newtons. And then the second one, net force is ft2 minus ft1 minus mg. Why? Because ft2 is up, the other two are down. Therefore, ft2 is positive, the other two are negative. Either way, you could have taken it backwards, it's okay. Like if you had taken these two positive, this negative, it wouldn't change the answer. Therefore, FT2 is FT1 plus mg. We already got FT1, 31 plus 31 now, 62 newtons. This you could have simply done just by taking the total mass multiplied with 9.8, isn't it? But I'm trying to follow a particular method. Understand that. We could simply have just multiplied, 6.4 times 9.8, you would get the answer in this case. All right, do the B part. Do the B part. The only difference, as you can see, is instead of setting it to equal to 0, now you have got to set it to equal to MA. Isn't that the only difference? Yeah, last time A was 0. That's why the whole right-hand side was 0. That's a simple thing. We've done this a couple of times now, so let me just speed it up. So times G plus A. We know that the tension is going to be greater, and you get 36.5 newtons. And the top one, again, plus m times a. That is the additional factor. I'm trying to show you that in place of 0 here, you have m times a. Therefore, you have an additional factor here. That's it. So that will give 36.5 plus 31.4 plus no space, so I have to take it out. 3.2 times 1.6, and finally 73 newtons is the 14 kilogram lawnmower. Two words caught my attention. What's this? What is that? What's the acceleration? Good, remember that. So it's moving, but still the right-hand side is going to be 0 because there's no acceleration. And 88 newtons is the force applied directed along the handle, which is at an angle of 45 degrees. Draw the free body diagram showing all the forces. One force, the weight. The other is the normal reaction. 2 came up. The third is the force of push. The fourth is friction. That's it. Those are the 4 forces acting on that object. Did I put the arrow on the friction, or maybe I stopped it just before? Or maybe I did not. Okay, let me put it now. Isn't friction that way, to the left? Yeah. So those are the 4 forces acting. Then it says, calculate the horizontal friction force on the mower. Okay, friction. To calculate friction, you'll have to start with the net force along the X. As I told you, it's now I've drawn FP cos 45 minus friction. Is that right? Because he's pushing? Okay. The 2 components, you see it there, FP sine theta and FP cos theta. So again, it is 0 because he's moving it at constant speed. Therefore, friction is, you rearrange that, FP cos 45, which is (62.2 newtons). Did you get it? A little different from what I was telling you, because I was saying that it was moving, right? In this case, there's no acceleration. Then when you consider the net forces along the y-axis, you have Fn, mg, and you also have Fp sine theta. Set it equal to 0 because it's not accelerating along the y. Make Fn the subject. When you plug in the numbers, it's 14 kilograms times 9.8 plus 88 sine 45. That gives you 199 newtons there. So that's A, B, and C. He was moving it at constant speed, and then he saw that the rains are coming. So he decided to finish it faster. So he's now accelerating. You see that? He said, no, this is not going to work. He starts running now. So that's what is happening in the D part. Doesn't he have to apply a greater force if he's going to accelerate it? Yeah, you know that. So how do we do this? A greater force, D part. What's the initial velocity? 0. What's the final? Did it say that the final velocity is 1.5? Because I cannot see the question anymore.
Yes.
Okay, 1.5 meter per second. And so the time was given in 2.5 seconds. And so you calculate the acceleration. And the equation is V2 is V1 plus AT. You find the acceleration, which is 1.5 minus 0 by 2.5. And you get the acceleration. And after that, again go back to the net force along the x-axis. It's Fp cos 45 minus friction. The only difference is the right-hand side did not become 0. That's all. That's all. The right-hand side is going to become 14 times 0.6. That's the difference. Let me finish. Well, so we're looking for the force that he must apply. In fact, on the whiteboard, I did that same thing, didn't I? Was the same thing. On the left-hand side, you can see that. So we already know the friction is 62.2, 14 times 0.6 divided by cos of 45. And now you see he has to apply 99.9 newtons. What was the force before? Was it 60? 62.6? 66.2?
62.2.
Both of you have two different answers. 62.2. I see that also. So, do you see that the force has increased? Definitely. To keep it moving at constant speed, that's all he had to apply. If he has to accelerate, he has to apply a bigger. Yeah, I know you're still thinking, not writing, right? How should this, after having said all this, how should this guy, or what angle should he push at to get what he's intending to get? Should he push at an angle of about 60 degrees, 45, 30, 20? I gave you so many options to get what he intends to do. What's he intending to do? Is he intending to go up along the y-axis? No. He's intending to go along the x. So he's looking for a bigger force component along the, and the maximum force component along the x would be if he's pushing at 0 degrees. But then there is a problem. There's not enough friction. He'll slip. Be with me on this. See, that is, theoretically, that's the best if he pushes at 0, which nobody can. So let's say 5 degrees, that's not good because now his friction is reduced. Did you understand? So now he has to find a balance between the two. I'm not saying he must push at 45. It comes by practice. It comes by practice. They know that they cannot stand like this and take off. That's useless. So they get it by practice and they say, okay, I need friction and I need a maximum x component of the force. So all that goes into running. Although they don't calculate it, they get it by practice. So it's a 75 kilogram sprinter. He's exerting a force of 720 newtons at a 22 degree angle with respect to the ground. What was the horizontal acceleration? So that word is important. That means we only look at the horizontal component of the force, correct? Okay, let's go because we have less time now. He's applying a force that way, 720 newtons, backwards. Of course, he's pushing back on the ground because he thinks he can push the ground back. But the reaction is what is propelling him forward, remember? You break that force into the two components, you get 720 sine and 720 cos. I should have broken up the reaction into the two components, but you understand that, isn't it? See, this force is going to have a reaction along this direction. And if I had broken that into two components, it would have made more sense to you because isn't he moving this way? Yeah, but it's the same thing, magnitude-wise. So net force along the x, 720 cos 22. That should be equal to mass times acceleration. Why didn't I consider friction at all? Because the problem assumes there is no friction. Do you see any word about friction there? Come on. Nothing. So that means you assume it's frictionless. So, but that is not a real case. You know that. Okay. That's why you only have that. So it becomes an easy problem. A is 720 cos 22 divided by his mass. Have you seen those printers? They are really lean. Have you seen them? Now you know why. Look at this. Where's the mass? The mass is in the denominator. Do you see that? So when that person is really lean and light, if he applies the same force as the heavy one, he gets a much bigger acceleration. I don't think I've seen. That's why when I see those football players, quarterbacks who are able to run, like the other day, goodness, it's not like. Okay, the B part, what do you have to do? If the force was exerted for 0.32 seconds, with what speed did the sprinter leave the starting block? Okay, tell me what you got to do.
The initial?
That's what we're looking for, right? So V initial, question mark. Do you know the acceleration?
Yes.
Yes. Aren't you given the time?
Yes.
Mm-hmm. Okay, wait. Are we looking for the initial speed or are we looking for the final speed?
Initial speed.
Yeah, I know you're going by with what speed did the sprinter leave the starting block. You're looking at that and you're saying it's the initial. But I'm looking at when you were standing there, what's his initial speed? And then with what he takes off is what we're looking for. That becomes the final speed. Are you with me? Otherwise, it makes no sense. His initial is 0. And the question says, with what speed does it take off? It's just like when I have that ball in my hand and throw it up. Is the initial velocity 0? If I throw it up, is the initial velocity 0? No. Thanks. Same thing. If I drop it, yes, the initial velocity is 0. Same thing. Okay. So we're looking for the final, is what I'm trying to say. Delta t, 0.32, v1 is 0. Looking for the final velocity, acceleration is given 10 meters per second. Go ahead. Use this equation, find, I thought I should make it more accurate. You see 10.27, I changed that to 10.27 because that was the number we get. You get 3.286 meters per second. As people have, velocity. It's not fussy dies, but you have, I don't know. What? Stuff hanging. And when you're accelerating from a stoplight, what's happening to whatever is hanging there? What is happening? Will it go backwards or forwards? What a silly question. When you're accelerating from a stoplight and the thing that's hanging from your rear view mirror, will it go backwards or forward? Backwards. That's what this problem is talking about. All you got to do is find the angle that the string makes with the vertical, right? Go ahead. I'll give you 2 minutes. Okay, here it is. The weight of the object acting vertically down, tension in the string up at an angle. And you're asked to find the angle with the vertical, that's why I've labeled it here. And then break it up into its 2 components. Does anybody know what this angle will be? Will be the same. Because you have parallel lines cut by a transversal, alternate angles are equal, right? That's what it's called. So, therefore, the vertical component is going to be cos. And the horizontal is FD sine. Diagram complete. And then you go back and say, well, we cannot finish this problem unless we know the acceleration. All right. Stoplight. So what's the initial velocity? And the final is 28. And the time is right there. Can't you find the acceleration now? Yes, you can. So that's what you do. So initial velocity, you're looking for the final, time is 6 seconds, you find the acceleration. And of course the equation is just dv by dt. Change so that, oh, it was 28. I wrote something here. 28 minus 0 by 6, that is 4.67 meter per second squared. And then you take the net force along the, I'm going to ask you this. What's the net force along the x-axis? Again, what's the net force? Remember, we're not considering air resistance, right? We're pretending there's no air. Only Ft sine theta, that's all. There's no other force along the x, therefore set it equal to ma. But first I'm writing the force along the y, so let me ask you about that. What's the force along the y? Don't you see too? Yeah, Ft cos theta minus mg must be equal to 0 because there's no acceleration along the y. That gives us Ft. And you get equation number 1. But you know what the problem is? The problem is we could have worked it out, look, from here. Watch this. But do you know what Ft is? Come on. No. Okay. Do you know the mass? Is the mass given?
No.
Oh, so you have two unknowns here. So it won't work. See? That's why you have to get the other one. So look at the x now, like I told you. There's only one force along the x, set it equal to m times a, which is max, means acceleration along the x. So now you get the second equation. What I did is this. Some of you understood, maybe. I wrote this on the left side. You make that out, correct? I wrote this on the left side. On the right side, I have what? Ft times sine theta. And I know Ft is all of this, isn't it? Therefore, I substituted for Ft, mg by cos theta times sine theta. Then I know sine theta over cos theta is tan theta. Now I see m on both sides. I can cancel out the masses. Maybe I didn't want to do it there. Okay, I did. And then ax is g tan theta is ax by, oh, now I cancel. Okay. X by g, 4.67 by 9.8. That's tan theta. Take the arctan of that or the inverse of that and you get the angle as 25 degrees. So can this method be used to find the velocity of a car?
We just used the-
Wait, can we use this method to find the velocity of a car? What if the car is not accelerating? How will that thing be? It'll be vertical.
Zero.
It'll be vertical. So the answer is no, you cannot, because unless it's accelerating or decelerating, you will not get an angle. So whether you're moving at 75 miles per hour or you're moving at a constant 50 miles per hour, both these cases, it's going to be what? Vertical. So how do you know? You don't know. So the answer is no. So I could have asked you a concept question based on this. And you should have said, if you understood, no. And then you should have said, yes, we can find the acceleration or the deceleration. And that will give you your 2 points.